In this video, we're going to study the first fundamental theorem of calculus. Now, let's first review what does the second fundamental theorem of calculus tells us. The second FTC tells us that if a function f is continuous on an open interval containing a number a, then the derivative of this integral will be equal to little fx. Now, this integral, we said it represents a combination function, capital Fx. So that's been said, the derivative of this capital Fx equals the little fx. And according to the definition of antiderivative, we can say that since the derivative of capital Fx is a little fx, therefore this means the capital Fx is an antiderivative of the little fx. Okay. Now let's take a look at this case. So now I have a function y equals fx and graph. Its graph looks like this. So I want to define an accumulation function. Actually, I want to define two accumulation functions. The first accumulation function I define is capital F of z1. Now z1 is a variable. So the function is defined from 0 to z1, the integral from 0 to z1 fx dx. Okay, so the function value is represented by this region. Okay, and then I define a second function f of z2. So that function is from 0 to z2 fx dx. And this function is represented by my second function is represented by this area. So this right from 0 to z2. Okay, now then the difference between these two functions gonna be the difference, the region, this green region minus this this blue region. So that will be okay. So that will be only this region, this area. Okay. Okay, and from the definition of a definite integral, this region, the area of this region, we can represent it by using a definite integral from z1 to z2 and fx dx. Okay. Now, if I change these two variables into two constant, this is A, now this is B. Then once we change the variables into the constants, we can have this result, which is a capital F of B minus capital F of A equals the integral from a to b fx dx. So this is the result of the first fundamental theorem of calculus. It says if a function f is continuous on the closed interval from a to b, and f is an antiderivative of little f on the interval, then this definite integral from a to b fx dx equals capital F of b minus capital F of a, right? So capital F is the accumulation function, and since the derivative of capital F equals little f, so capital F is an antiderivative, right? This is what we know from the second fundamental theorem of calculus, right? So this means if a function is continuous on the closed interval, then when we evaluate a definite integral like this, we can use this strategy. And this strategy is we first find out what is an antiderivative of little f, which means we first find out what is a capital Fx. And then we calculate the difference between these two numbers, capital F of b and capital F of a. Now you can see, using this method, it will save us a lot of time. Because if you recall the methods we used in the previous lectures, we said when we evaluate a definite integral, we use the limit of Riemann sums, right? And using that method, you have to do a lot of work. Okay. So now, using this new method, we only need to do two things. First is to find the antiderivative, and the second thing, we plug these two numbers into the antiderivative and then find out the difference. Okay. Let me use this example to illustrate this method. So here we are asked to evaluate the integral from 0 to pi cosine x dx. So first, we need to know what function is an antiderivative of cosine x. In other words, we want to consider this problem, which function capital F, when I take the derivative of that function, the derivative is cosine x. And since we know when we take the derivative of sine, since the derivative of sine x is cosine x, therefore capital Fx is sine x. Okay, now then we need to calculate what does the f of what does the sine of b and the sine of a equal. So here, since now a equals 0 and b equals pi, so sine of a, which is sine of 0, equals 0, and sine of pi also is 0. Is it 0? Okay. So according to the result of the first fundamental theorem of calculus, this definite integral equals sine of pi minus sine of 0, which equals 0 minus 0, which is 0.